the dynamic set pieces side of things. So this presentation is going to be if you're creating a stage show and are submitting your engineering calculations for one of your dynamic, i.e. moving, set pieces. Make sure before you watch this video that you review the overview video. That'll kind of set the precedent for all these things that we're going to explain in here. Alright, so what are the sources of energy for our dynamic set pieces? We've defined that we have this kinetic energy and this potential energy that are going to change our system dynamics. But we need to be able to apply those to what the dynamic set piece is actually doing. So for our kinetic energy, we have the forced movement of the piece. And the potential energy, we have the mass of the piece. So to kind of take it to an existing stage show, on our right here we have a snapshot from Frozen and Live at the Hyperion with no comment about the quality of the show. We have our moving staircase for Elsa. Now this moving staircase moves at a velocity that's determined by a laser guidance system, as well as has a mass, that includes this base here, and then the entire staircase. And something that they also had to consider for this piece is a performer. So the mass of their system included their base, the staircase, and the performer. So those are kind of our two ways that our system will function. Now let's kind of take a look at what we're going to do with those parameters to get our results. So how much energy does it take to tip a set piece is what we're going to start with. We're going to see how much it's going to take, then we're going to take a look at how much we have. So let's look at some geometry of the system. This is just a box. Your set piece can be any shape or size, but it's always going to have this little red circle. This red circle is called a center of mass. The center of mass is a location on the set piece where we bump up all the mass of the system and achieve relatively similar dynamic results from that simplification. For dynamic set pieces, what I want you to consider is I want you to go ahead and take each component of your set piece and kind of estimate its mass and see how far away it is from everything so that you can kind of balance a scale. Now, your center of mass is going to be at the center point of that balance. So say you have a set piece and it kind of looks like this. It's got this big back on it, and then it drops off in the front here. Maybe this is some kind of mirror on the back side. So we have a lot of mass back here and not so much mass back here. So our center of mass is probably going to be somewhere right around here. All right? Does that kind of make sense? You're kind of estimating where the center of mass is based on the profile of your set piece. Now, once you've done that, there are two things you need to determine. You need to determine the height, where I just drew over this H1 here, off of the wheels, and also the distance to the nearest wheel. So this is what we're going to call L, and then this is our H1 that I crossed out here. So what does it take to tip something? Well, in order to tip something, the center of mass has to move above the tipping point. At this point, we have what we refer to as an unstable system, and any more change in the system will result in a tip. So we're going to call this H2. This distance such as that the center of mass is above the tipping point. Now we kind of see that we've got this right triangle here, where H2 is the hypotenuse and H1 is the height here, and then right here we have our length L. So what this tells us is we can analyze this using the Pythagorean theorem to get H2. And just a quick reminder on the Pythagorean theorem, we have H2 squared equals H1 squared plus L squared. So we can solve that for H2, and that way we have H2 in terms of our system parameters, H1 and L. So, just to recap, in order to tip the system, we need to move the center of mass above the tipping point. Because we have one rigid body that's all going to move together, in order to do that, the height change will end up being H2 minus H1. And that's because the center of mass is originally at this height H1, and moves to this final height, h2. So we're going to kind of recap this in the next slide and start applying it to our formula. So we have our original formula here, U equals mgh, and like we just said, that height difference is h2 minus h1. And now we want to make the substitution using the Pythagorean theorem that h2 is the root of h1 squared plus L squared, where once again L is the horizontal distance from the tipping wheel to the center of mass. Now if we substitute all of that back in, we get this formula, where the potential energy is simply a function of the position of the center of mass. Now this is exactly what we want. We've gotten our potential energy all in terms of parameters of our system. In the spreadsheet, you'll find that you can just input the location of your center of mass and it will automatically determine the potential energy for you. Alright, so we kind of have what we'll call our allowable. This is the amount of energy that is required to make the system do something we don't want it to do. So it's the maximum energy we can have in our system. Now let's talk about what we're going to apply to the system. And that's going to be our kinetic energy. Just a quick reminder that the kinetic energy is equal to 1/2 mv squared, and that v is the velocity you plan to move your set piece at. So if you don't have any kind of idea, 1 meters per second is a good estimate of what you might do. That's pretty standard across a couple of different places. So now here's kind of the catch and where we're going to be doing our quote analysis. We need the potential energy that we calculated back here to be greater than this kinetic energy. So what does this mean physically? If the potential energy required to move the center of mass from h1 to h2 is greater than the kinetic energy given by the system dynamics and the movement of the piece, it means that the center of mass cannot possibly, in any physical way, gain enough energy to increase in this much height. So that means that this piece, under normal operation, could not physically tip. So this is something really, really cool. A way that we can, directly through the dynamics of our system, say, hey, it is physically impossible under normal operation circumstances to tip this piece in its operative performance. So that's kind of our explanation. You should be all set up now to use the Excel sheet. For this, you'll use the mass that you estimate for your piece, as well as the velocity that you estimate for your piece. And like I said, use 1 meter per second if you don't really have any clue how quickly you need to move that on or off the set piece. This is a maximum linear velocity for my engineering type friends, and is often the maximum of linear induction motors planted in the base of your stage. So that's about where we want to go. So the Excel sheet is going to be available for you to take a look at. If you have any further questions, feel free to reach out to us. We'd be happy to answer them. And if you'd like to learn a little bit more about what's going on here and some of the further dynamics of dynamic set pieces, feel free to shoot us an email.